Hi, I'm Anthony Ostiuni, and I'm here to tell you about some recent joint work with Daniel Kane and Kelwin Wu on locality bounds for sampling Hamming slices. Now, traditionally in complexity theory, we study what computational resources are needed to evaluate a function on any given specific input. Alternatively, you could ask about the case when I feed a computational model with sort of random inputs. Well, this will generate a output distribution. And now I can ask, what computational resources do I need to output a specific distribution, or at least approximate it? Now, this idea appeared in some earlier works, but was largely popularized in the last decade by a seminal work of Viola, motivated by applications to data structures. Now, a standard example is the parity function. Parity is notorious as being a difficult function for shallow circuits to compute. However, I can do a similar task very easily. In particular, I can produce the uniform distribution over input-output pairs as follows. For each output bit, I'm simply going to XOR two of the consecutive random input bits and have them overlap in such a way that when I jointly XOR everything together, only the first and last input remain, and their XOR becomes the parity evaluation. Now, our general goal here is to better understand the capabilities of various circuit classes for these sorts of tasks. The computational model that we'll study in this work is categorized by locality. So we'll say that a function is d-local if every output bit depends on a most d input bits. Now, this is a meaningful definition because d-local functions encompass circuits of depth order log d and bounded Fanning. So in particular, constant locality functions encompass NC0 circuits. If this is the picture we have in our heads of the computational model and sort of the input and output structure, working with locality is also nice because we can think about things in a bipartite graph structure where each vertex in this set of vertices corresponding to the output has degree at most d, assuming that we connect an input and output if that output depends on the input bit in some way. Now we'll fix this definition of f for the remainder of the talk as some d-local function between m-bit strings for some arbitrarily large m and n-bit strings. The parity example was nice because we were able to exactly output the distribution of interest. But sometimes this is too much to ask for and we have to be happy with approximations. Now in this case, of course, we need some distance measure to quantify our approximation, and we use the standard total variation distance. The notation we'll use for the remainder of the talk is this script u to the m to denote the uniform distribution over m-bit strings, f of this as the output distribution of our function f when fed with these random bits, and this script dk as the uniform distribution over n-bit strings of Hamming weight equal to k. As mentioned, there is some earlier work in this area, going back to Viola in 2012, who proved logarithmic lower bounds on the locality in the case of the uniform distribution over strings of weight n over 3 or n over 2. However, these results came with the assumption that the input length is bounded, and ideally we'd like unconditional lower bounds. Much more recently, Viola was able to raise this assumption in the case of weights n over 3, and Filmus, Ley, Ryazanov, and Sokolev were able to prove similar unconditional bounds in the case of small k. Our main contribution is the first super constant lower bounds in the case of weights n over 2 or 0 mod 3. It should be noted that upper bounds are roughly logarithmic, and we suspect that this is closer to the correct answer in these cases. Let me briefly outline the remainder of the talk. We'll first show lower bounds for the 1/3 bias distribution. This is the distribution where each output bit is 1 with probability 1/3 and 0 otherwise. Then we'll show similar bounds on the uniform distribution over strings of Hamming weight n over 3 We'll take a detour to show a separation in classical versus quantum complexity, and then return to the more complicated cases where the weights are n over 2 or 0 mod 3. Finally, we'll show an application to succinct data structure lower bounds, and finish off with some upcoming and future directions for this work. So let's begin with the 1/3 bias distribution. A similar result to this theorem was originally implicit in a previous work of Viola. However, we were unfamiliar with it and ended up reproving some things. But in any case, it will be a useful warm-up for later work. So here's sort of the picture to have in our head. The inputs on top, the outputs on the bottom, where each output depends on at most d inputs in any arbitrary way. And let's focus just on one specific output, say y3. And additionally, let's say that all the inputs that affect y3 belong to some set S. Okay. Well, if you calculate the expectation of y3, it turns out that this has to be sort of an integer multiple of 2 to the minus d. However, a key observation is that 1/3 can only be expressed by multiples of 2 to the minus d to some error approximately 2 to the minus d. And so this sort of projection onto a single output coordinate inevitably has to have some error. Now this is not a substantial amount of error, and so if we want a stronger bound, we'd ideally hope to sort of combine a lot of these independent marginals together. And this is in fact what we do. Right? So we'll say that output bits are independent if they don't depend on the same input bit. And then using sort of standard concentration inequalities, you can show that if we have r independent output bits, we get the following error. However, we of course have to handle the case where no two output bits are independent, right? One can imagine that, say, x4 affects every single output bit. Well, the way to get around this is by conditioning on the value of x4. In particular, we can write our output distribution as an even mixture of the case when x4 equals 0 and when x4 equals 1. And now we sort of want to reason about these restricted functions and combine everything back together at the end. So more precisely, you could show that if you have sort of t of these restricted functions that are far from what they should be, their convex combination remains far from what it should be. And this follows essentially by a union bound. So at this point, it remains to determine what input bits to condition on, or how many at least we need. And for this, you can view it purely graph theoretically. So as we've mentioned, you can view the input and output structure as a bipartite graph. And now our task is to remove few input bits to obtain many independent output bits. Or more quantitatively, we want to delete about r times 2 to the minus d input bits, as long as we can find r independent output bits, where things are optimal if we make r as large as possible. And it turns out that we can solve this task with r about n over 2 to the d squared, and this is tight. I'll skip the proof for time's sake, but combining everything together, we get the claimed result. So just to recap here, we first use graph elimination results to obtain many independent output bits. Now each of these output bits necessarily has some error, and we can accumulate these errors together by independence. Now, using very similar ideas, we're able to prove similar bound in the case of the uniform distribution over n-bit strings of Hamming weight n over 3. Let's go over our first application. We'll call that NC0 circuits, or NC0 is the class of circuits of constant depth and fan-in, and QNC0 is just the quantum analog of this. Well, sort of a driving research direction in quantum complexity theory is when does sort of using quantumness gain you some advantage. And so Bravi, Gasset, and Koenig ask the question in this setting of, when are QNC0 circuits more powerful than NC0 circuits for our sampling task? Very recently, Watts and Parham showed that there exist distributions that are sampleable within distance 1/6 by QNC0 circuits, but any NC0 circuit is at least 1/2 far from. But however, this assumes, again, that the number of random bits used is bounded. And this is the same restriction that came from the earlier work of Viola we mentioned. Well, this 1/3 lower bound that we just showed gives the immediate corollary that we get some lower bound that exponentially decays. It's just kind of the best you could hope for. And on the other hand, there's a simple observation that QNC0 circuits can perfectly sample or perfectly simulate a 1/3 bias coin. And so this gives us, an optimal separation in this case. In some sense, right, this doesn't feel like the most satisfying answer, because the separation seems to come more from like binary precision issues than from quantum power. But I'll defer you to our paper for a slightly more detailed discussion on this. Now let's handle the more challenging case, where the weights are n/2. Previously, our plan was to find independent output bits, show that each has some error, and accumulate them by independence. However, it's not necessarily true anymore that each output bit has some error when our weight is, say, like n/2. And so we need to be able to handle the case of many independent, unbiased output bits. Well, one way we might hope to do this is to use anti-concentration. And this has been useful in sort of a similar work previously. So in particular, a standard fact is that if I have, say, R independent Bernoulli random variables, right, they don't sum to any particular value with high probability. They're very spread out. Right? And this seems like it would pose some problem or give us some lower bounds, because our goal is to produce a distribution where the weight is exactly fixed. So we can try to make a new plan here and do what we were doing before. But now, if we have the case when many of these marginals don't have error, we get many unbiased bits, well, now we can hope to use a large error via anti-concentration. So are we done? Well, unfortunately not quite. Consider the following example. In some sense, this is like all you could hope for, right? We have n/2 completely unbiased bits, but they sum to a fixed value, to n/2, regardless of the specific values. Okay. And the issue here is that there are some correlations outside of the independent set. And so pictorially, we chose y1, y3, y5, for example. These sort of get counteracted by their adjacent pair. And one way we might hope to handle these correlations is to modify the desired structure we're looking for. So rather than just look for independent output bits, now we're going to look for what we call neighborhoods. So say the neighborhood of an output bit is just all the other output bits that share some independent bit dependence. Excuse me, some input bit dependence. And now when we move from just bits to neighborhoods, right, we kind of repeat our plan. If I can find many independent neighborhoods that are far from uniform, well, we can do what we did in the, say, n/3 case, and show that there's a large error by independence. Otherwise, there are many uniform independent neighborhoods, and we can get a large error via anti-concentration. Now, I should say there's some subtlety that I'm sweeping under the rug here, in that the weight of a neighborhood can still get fixed by outside correlations. However, because we have this stronger structure, we have better control over things, and we can reason that it's very unlikely that this weight gets fixed. So this isn't actually a problem. And so again, we're going to use some sort of graph elimination result to find what input bits to condition on to achieve our desired structure. Now here we're looking for a stronger structure, so it turns out that we need to condition on much more bits, and now we get sort of a tower and D type dependency. A bit surprisingly, this poor dependency does seem to be tight for this at least the graph theoretic subtask. So okay, combining everything together, we get the stated theorem. And using similar ideas, but using sort of a modular anti-concentration result, we also get lower bounds for the case of say the strings are weight 0 mod 3. And note that both of these results are tight for constant D by considering the uniform distribution. Let's now discuss an application to succinct data structures. So say I have some subset of all n-bit strings, h, and I want some way of storing an element of h such that I can check the ith bit. Well, one easy way to do this is to just store a as is, as an n-bit string, and then if I want to check the ith bit, I just look at the ith bit. So this is easy to query. However, it's not the most efficient way to store these strings. So alternatively, I can compress our family down to the information theoretic minimum, and this is now very efficiently stored. But if I want to learn the value of AI, well, at least naively, I'd have to read the entire string. And so sort of this area of succinct data structures asks about getting the best of both. We want to store things efficiently while still making them easy to query. The specific problem we're interested in here is a dictionary problem. So given our family H and two parameters S and D, we'd like to be able to store an element of H in S bits, where the ith bit can be determined by at most D non-adaptive queries. And there's a really nice connection noted by Viola, saying that, okay, if we have a solution to this dictionary problem, then there exists a D local function, f, from S bits to M bits, such that the output of this function is close to the uniform distribution over H. Right. And so this is sort of an upper bound on the distance. We've previously proven some lower bounds, and so when you combine these, you get consequences for such data structures. So, I mean, you can combine this with any of our results, but as one example corollary, take H to be the set of all n-bit strings whose Hamming weight is 0 mod 3. Well, then this will tell us that the dictionary problem for H needs either n bits of storage, which is sort of the trivial algorithm, right, or a super constant number of bit probes per query. And so again, this tells us that sort of the only data structure using constant bit probes is the trivial one. And again, we emphasize that this works for more general modulus and other results. This is just one example. Okay. Let me conclude with some upcoming and future directions. One thing that you could ask about is to restrict yourself to the case of constant locality and say, okay, what can I sample in this setting? There's a really nice conjecture by Filmisley, Ryazanov, and Sokolov. It says that if my output distribution is close to some uniform symmetric distribution, then it's in fact close to the uniform distribution over strings of Hamming weight belonging to some set. So either sort of the all zeros, all ones case, the even mixture of the two of them, strings of uniform, sort of uniform over strings of even weight, uniform over odd weight, or uniform over everything. Using similar ideas to this work, but with some new ideas as well, we're able to confirm this conjecture and a bit more in an upcoming work. One problem that we're not able to handle is to improve these locality dependencies. Right, so right now we have a pretty large gap, and this stems from our graph elimination techniques, which, as mentioned, these are tight. So somehow, if you want to beat our bounds, you might need some new ideas to do so. And a final direction is to consider now distributions with non-symmetric support and see what you can say about these. So yeah, it seems like there's a lot of sort of exciting work to be done in this area, and I look forward to seeing what other people do as well. Thank you for listening.